Okay, so welcome to today's video about speed and velocity. When we are talking about speed and velocity and motion in general, it is important to remember a few terms. So let's start with those. And I know you know this, but there are a few distinctions here that are going to become super important. So first of all, the first motion term that we want to talk about is position. Position is what we will be using rather than distance, because position says where we are from an origin, from a frame of reference. So where an object is from a point of reference. Now, granted, distance tells us that as well, except for the fact that distance may sometimes be talking about what we call the path length. So if we went, for example, if our origin is here and we were trying to get over to here, our distance could have been that whole path length. But if I want to know where I am in relation to where I started, then that's not going to be helpful to me. And instead, sorry, let me just make a note here that could be distance, or instead, let's change this to being that for the moment. When I talk about position, I'm talking about from here, straight line to here, what is my position? So one of the things that you're going to notice in this semester is that I'm going to be very particular about what words you use to describe different types of motion, because while they are in our regular normal voice, they mean the same thing. In physics, they actually have differences between them. So when we are talking about where we're at compared to where we started, we want to talk about it in terms of position. Similarly, we want to make sure that we continue to use position in terms of x's and y's. So for our horizontal displacement or our horizontal motion, we will use x. If we're moving up or down, we will call it our position in the y direction. Okay. We use the same units. Some places you'll see the books referring to position as d for distance or s. I would prefer to keep with x's and y's, and then we can be positive of what direction we're actually talking about. Now, one of the other things that we want to talk about as well is what about our change in position? So what if we, like I said, we start here on the left at point A and we come over here to point B. We may very well have taken this path that I've labeled distance to get from A to B, but if I want to know actually that specific straight line distance from A to B, then it has a different word for it, and that is called displacement. So displacement is a very specific word in physics, and it means a change in position. Doesn't matter how you did that change in position. It doesn't matter how crazy the path was. It just means that it is a change in position. And that's important. So, for example, if we are talking about having gone from A to B, then we could have a positive displacement. If we are talking about going from B to A, we would have a negative displacement. But if we are talking about distance, the distance from A to B is exactly the same as the distance from B to A. So we can't distinguish in our terminology what we're talking about if we don't use displacement rather than distance, because the distance is the same. But with displacement, we can be specific as to whether we're going in the positive direction or in the negative direction. So from here, let's take a look at some graphs again, and let's see how we can discuss them a little bit more in detail using a little bit different terminology here. So let's turn the page. Let me put a graph up. Let's have this be our x, this be our t. And we have two objects on the same graph. So we're plotting the motion of two objects on the same graph. If we want to describe this motion in detail, you want to be very specific about the terminology that you use. So for example, object number 1 is traveling. How? Well, let's look at it. We know that it's not starting at the origin because it's down here. Rather, it's up here and the origin is down here. We also know that we can call, because we talked about this last week, we can call that position where they both started x naught, the initial displacement or the initial position. So we can say that x naught is equal to the original position. Because the slope is increasing, we know that it's going away from the origin. Neither one of these objects has a slope that is changing, so that means that the speed is the same. It's changing its position at a constant rate. So it's moving to the right of the origin with a constant speed. Be careful in saying just the simple slope A is greater than slope B, or slope 1 is greater than slope 2, because that's very vague. It is true, but it's very vague, and it doesn't tell me that you know what you're talking about. So rather than using that terminology, rather than saying that slope 1 is greater than slope 2, let's be more specific. Let's say that, what does slope represent? How do we get this, and what is it talking about? Well, this is going to get us into what we're going to talk about this week in class, and it's not quite in the order of which I wanted to do things. I wanted your lab to be able to get you to this, but since we had to change around our order of labs, let's not worry about that, and let's just go ahead and talk about this now. So the slope of a line, in particular this line. Let's look at slope 1, for example. We know that to get the slope, it is the rise over the run. The change in the y values over the change in the x values. Well, let's look at what our y and x values are then. On this graph, our y values are displacements or distances or positions. So our change in y value for this graph is actually a change in position. Our change in x value is a change in time. So our slope is change in position over time. And you already know what that is. You've already done this beforehand on some of the other problems that we've been talking about. But I want to be explicit now because we're really going to be starting to derive our kinematics equations in this manner. So if slope is change in x over change in y, and we know that our position over time tells us how fast we're going, then the slope of a position time graph will give us the speed. This is big. And what this means is that it's going to really give us an average speed. We'll get into more detail in a minute as to why this is or isn't velocity, but right now, let's just talk about it being for speed. The variable we use for speed is a v, so our speed is change in x over change in t, which again, keep in mind, this is our slope. So the slope of a position time graph gives you the velocity or the speed. Well, in this particular case, our position has an initial value that is not 0. So if I want to come up with the equation of this line, then I need to be a little bit more specific about that. So let's look at delta x. Delta x is the change in position of the object. Well, we know that the object started at x naught, and it ended up here somewhere at a position x of f, the final position. So I can change my delta x here in this equation instead of writing delta x to being x final minus x initial over delta t. So now we're getting a little bit complicated in this equation because we now have that v, our speed, is equal to our final position minus our initial position over our change in time. We're going to leave change in time as change in time, sort of, but we're going to make the assumption as shown here that we're starting at t equals 0. If we are starting at t equals 0, then our change in time is really just however long this occurred for. So for this example, it is just simply whatever that t is. So my speed then, I can change this one more time to say that my speed is final position minus initial position over time. This is, in fact, one way that you can write your kinematics equation for speed and time, but it's often not written like this. We don't typically leave our equations as fractions, although it can be written like this and it can be saved like this and you can use it like this. But let's write it out in a way that is more representative of what this is showing. Because this is a straight line graph, we can use this in terms of y equals mx plus b. So when I do that, remember I just had written that v is equal to x final minus x initial over time. Sorry, over time. In my equation, y equals mx plus b, my y is the x value. My x is the time value. My intercept is the initial x. So I can rearrange this to say that position is my speed times time plus my initial displacement, how far away I am from the actual origin. This is our first kinematics equation. If we find that we actually started at the origin, then we don't have an x naught, then we can go back and say, well, okay, so our displacement is vt. Either one of those works out really well. But this is the first derivation that we've really done of a kinematics equation. Kinematics equations are the names for all of the equations we're going to be looking at in the next few units. Kinematics means motion. So it's the movement of objects, and it's the laws that govern it. So I'm pretty sure that you get this and it's pretty easy, but I want to do another one, and I want to make a distinction now between speed and velocity. So let's do that. We already know that speed is how fast we are going. Or how fast an object is going. That's all we know about it. We know how fast the object is going. The speed tells us nothing else. It doesn't tell us if it's going to the left or to the right, north, south, anything like that. Backwards, forwards, it tells us nothing except for how fast the object is going. The problem here is that when we talk about speed, we also use a v. And it is still our x over t, but in this case, x is distance. Over time. So remember at the very beginning when we had that crazy path that we went on here, where we had the crazy path? If we measured that entire distance and divided by how long that entire crazy path took us, that would tell us the speed of the object that did that path. However, if we are just looking at velocity, then when we look at just velocity, velocity takes into consideration your direction as well. So every one of the ups is canceled by an equal amount of down movement at the same speed. So while your speed is how fast you are, its distance over time, your velocity is really your displacement over time. There we go. Displacement over time. So with velocity being displacement over time, this means that it is not only how fast you're going, but it also includes what direction you're going. So velocity is speed with a direction. So the graphs that we've been making that have had part of the velocity graph on top of the origin line, on top of the x-axis, and part of it below, those really are velocity time graphs and not speed time graphs because they're showing that one's positive and one's negative. Let's take a look at how this works and how it looks in a graph and with a motion map as well. Okay. So first of all, let's take a look at this motion map. Let's assume that all those lines are the same length because I can't quite draw them exactly the same length. If this is our motion map and we want to describe this motion, then we can say that it is constant speed away from the origin and they started some distance from the origin. So they started some distance from the origin. So we could easily make a position time graph for that. And it would be very similar to ones that we looked at in class last week. And keeping in mind that it is not starting right here at the 0 point, that has to mean that there is an initial position. So when we make our graph of position and time, it's going to start here, and it's going to go up like that. We know that it goes for 0, 1, 2, 3 seconds like that. So we could make this quantitative if we want to. We could add 3 seconds to it and make sure that our line goes all the way up. Sorry, that's really not a good line. Let's try that one again. And then we could actually figure out specifically where each of these seconds was, where the car was at each of these seconds. If I want to make a velocity time graph from this, then I need to figure out the slope. So I can take this and I can go to a velocity time graph. This is a constant slope, so we know that our velocity is also going to be constant. If I gave you some more numbers, you could calculate it, but without those numbers, we can see that it is steady, so we can go ahead and put a line across, and that tells us that that's our velocity graph that goes with this position graph, which goes with this motion map. However, one thing that this velocity graph could also show is something a little bit different than that. You have to keep in mind that position time graphs tell you about the starting conditions very clearly, that there is an initial displacement. There is no way to show that on the velocity time graph. So keep that in mind, that your velocity time graph does not tell you initial conditions. So while that is what the velocity time graph would look like for this situation, it is also what the velocity time graph would look like for this situation. So be careful making sure that your position time graphs go along with not only the velocity time graph, but also your motion maps, so that they are representative of what you're really looking for. So again, if we take a look at this position time graph, this one here has the equation of x is equal to vt plus x naught, because v, remember, is the slope. This position time graph, which could also be represented by that velocity time graph, has a little bit different equation. It is simply that x is equal to vt, because it does not have a y-intercept. Its y-intercept is 0, and the velocity is still the slope. Okay? One other quick thing to tell you about that will be important and that we are going to talk about some more this week with the lab, but I want you to know about it now so you can be thinking about it, is what about if we start with our velocity time graph? If I have a velocity time graph like what I had on the last page, that it goes straight across like that, what can I find out from this? So really the question is, what does this tell me? Well, first of all, one of the things it tells me is that it is constant velocity. Another thing that it tells me is that the velocity is a positive value. So if it's a positive value, then this object is moving away from the origin. And that gives us a good clue, because there's one other really cool thing that we can find out from this graph that you probably haven't thought of yet. When we were talking about position time graphs, we said that the slope was the speed, because remember that slope is change in x over change in t, right? By definition, and distance over time or displacement over time is velocity. Well, if we take a look at this velocity time graph, we can't take the slope of it because it would be 0. It doesn't change any. But what we can do, oh, wait a minute. It doesn't change any. If its velocity doesn't change any, then that's an important thing. Then that tells us that we have a constant velocity, which we said, which means that it's not changing. Sorry, I didn't realize we'd already said that one. But what else it tells us is super cool as well. Let me change colors again here. So if I take my velocity time graph, velocity and time we already know are related to each other through the speed formula, that speed is change in distance over time. So what if I find out this? What if I look at the area under the curve? That's a nice rectangle. A rectangle is, the area of this rectangle is found by the length times the width, or the height times the width, whatever you want to call it. Well, the height in this case is a speed. So the area under the curve, or under the line, is a length times a width. Well, we just said that one of those is this velocity. The other one is time. Wait a minute. Velocity times time is the area under the curve. But we just said on the last page that velocity was distance over time. So if velocity is displacement or distance over time, what is velocity times time? It is the displacement. So velocity times time is your displacement. So what does this all mean? Well, this means that from a position time graph, we can get more information than what it appears. And from a velocity time graph, we can get more information than what it appears. So let me summarize everything that we've talked about in this video on the next page. First of all, if we have a position time graph, the slope of the line is equal to the velocity. So we know that v is delta x over delta t. If we go ahead and make a velocity time graph from this, then we're not going to worry about the slope of the line right now, but instead we're going to worry about the area under it. So the area under the line is equal to the displacement. And we said that that would mean that VT is equal to delta X. So there's a back and forth that we can do between position time graphs and velocity time graphs by figuring out the slope or figuring out the area under the curve. So keep these in mind. Also keep in mind the equation that we can come up with from both of these lines, which is that X is equal to VT plus X naught, and then your X naught, could be 0 if necessary. Hopefully this is a good reminder and will help you with solving some more problems, and we'll talk about why this is super important with our lab that is coming up tomorrow. Bye for now.